Hello and welcome back to the Science of Concrete Materials class. This is lecture number 29 of the class, and today we will start on the new module, which is the mix proportioning. In this module, we will define what is mix proportioning, discuss the basic considerations in mix proportioning, the steps followed. There's a methodical steps to follow in order to design the mix, and at the end we will have an example of a mix design. Okay. Okay, the proportioning of concrete mixture, or more commonly referred to as mix design, is a process that consists of two interrelated steps. First, the selection of the suitable ingredients, which are, cement, aggregate, water, maybe admixtures of the concrete. And the second is determining their relative quantities, which is basically the proportioning, to produce as economically as possible concrete of the appropriate workability, strength, and durability. These proportions will depend on the particular ingredients used, which will themselves also depend on the application where the concrete will be used. Other criteria such as designing to minimize shrinkage and creep, or for special chemical environments, may also be considered. Okay, so although a considerable amount of work has been done on the theoretical aspects of the mix design, it still remains largely an empirical procedure. And although many concrete properties are important, most design procedures are based primarily on achieving a specified compressive strength at some given workability and age. It is assumed that if this is done, the other properties, with the exception of the resistance to freezing and thawing or other durability problems, for example, such as chemical attacks, will also be satisfactory. So that's if we satisfy the strength at a particular age and a particular workability, then we will be fine. Okay, there's more to it than that, but at least this is the basic process that will get you to the starting point to adjust the mix any way you want after that. Okay. So basically, the criteria for the mix design are the strength, durability, and economy. Okay. So there are certain considerations that you need to consider when designing a mix. The cost of the concrete is basically made up of the costs of materials, labor, and equipment. However, except for some special concretes, the costs of the labor and equipment are largely independent of the type and quality of the concrete produced. So it is, therefore, the material costs that the most important in determining the relative costs of the different mix designs. Okay. Just as I said, mostly the equipments and the labor used will be independent of the type of concrete. So that as far as economy, mostly we're talking about the cost of the materials. Okay. So since cement is much more expensive than aggregate, it is clear that, minimizing the cement content is the most important single factor in reducing concrete costs. This can in general be done by using the lowest slump that will permit adequate placement, by using the largest practical maximum size aggregate and by using the optimum ratio of coarse to fine aggregates, and when necessary by using appropriate admixtures to improve workability. It should be noted, here that in addition to cost, there are other benefits to using a low cement content. As we discussed before and we will discuss later, shrinkage will in general be reduced when we reduce the cement content, and there will be less heat of hydration. Okay, if you remember when we discussed during the hydration of the cement. So if the cement contents are too low, they will diminish the early strength of the concrete and will make uniformity of the concrete a more critical consideration. So these things you have to keep in mind. When considering economy, you reduce the cement content, we gain in certain aspects, but on the other hand, we might lose. So that the balance you have to make. Also, the economy of a particular mix design should also be related to the degree of quality control that can be expected on a job. Okay, so the design, concrete strength must be higher than the specified minimum compressive strength because of the inherent variability of the concrete. So again, you have to account for less than perfect practices in the field. I mean, if you can guarantee 100% the quality control practices, okay, but it can never be guaranteed. That's why, the design strength will be higher than the specified minimum strength. Okay, so on small jobs, for example, it may be cheaper to over-design the concrete than to implement a quality control program, in conjunction with a more cost-effective concrete. So again, implementing a rigorous watertight quality control program in the field may not be cheap. So if it is not worth the effort on small jobs, over designing is much cheaper. Okay, I hope you get that. The second consideration is, workability. Clearly, as we have been talking, a properly designed mix must be capable of being placed and compacted properly with the equipment available. All right. Also, finishability must be adequate and segregation and bleeding should be minimized. Okay, we discussed the workability and its related properties in the previous module. So as a general rule, the concrete should be supplied at the minimum workability that will permit adequate placement. And for concretes without mineral admixtures, the water requirement for workability depends mostly on the characteristics of the aggregate rather than those of the cement. Remember what we said when we talked about the fresh concrete properties, and we talked about the aggregates also. So where necessary, workability should be improved by redesigning the mix to increase the mortar content rather than by simply just adding water or more fine materials. Okay? But remember, it's easy to add water, but it cannot be done like that. So the redesigning the mix, taking advantage of the available admixtures that will help improve the workability will go a long way. So cooperation between the mix designer and the contractor is really essential to ensure good concrete mix. In some cases, a less economical mix may be the best solution, as we said, because not trusting 100% the field practices. No, I would over design to make sure I would end up with the required properties than something else. And as just probably as I mentioned several times, a deaf ear should be turned to the frequent pleas from any job site for more water. Basically, we're talking here about small jobs. On bigger jobs, there is more quality control in place, and typically the use of admixtures will help eliminate the workability problem. Okay. The other considerations are, the strength and durability. So in general, concrete specifications will require minimum compressive strength. They may also impose, limitations on the permissible water cement ratio and the minimum cement contents. Sometimes you might see that just basically when reducing water cement ratio, meaning we are looking after durability. Okay, the cement content probably just to make sure we have, to reach certain strength at certain ages. Okay, also it is important to ensure that these requirements are not mutually incompatible. Okay, so that means it's not necessarily, the 28-day strength that is most important. Strengths are at other ages may control the design. Like for example, you need a strength at a certain age in order to strip the forms and reuse them. Or maybe if you are casting post-tensioned concrete, where you have to pull the cables at a certain age, maybe let's say 72 or 96 hours, so you have to reach certain strength. So the 28-day strength is not always the determining factor. Okay, also specifications may require that concrete meet certain durability requirements, such as resistance to freezing and thawing or chemical attack. These considerations may provide, further limitations on the water cement ratio or the cement content, and in addition may require the use of admixtures. So many things really to consider here. Okay, so the process of mix design then involves the satisfactory resolution of all the requirements just described. Okay, since these requirements cannot all be optimized, simultaneously, some compromise, as between strength and workability will be necessary. You have sometimes, to give up something in return for something else which is more important. All right, so it must be remembered that even a perfect mix will not perform properly unless the proper placing, finishing, and curing procedures are carried out. And again, we go back to the concrete practices in the field. Sloppy practices or less than perfect practices will compromise the best mix design out there. So that is a message to our field engineers and our construction personnel, just to always pay attention and follow the procedure. Okay. So let us just probably summarize what has been discussed just for the last few minutes. The basic considerations, to consider when designing a mix. Balance between all desired properties sometimes is not that easy to achieve. So you gain something, you give up something. Redesign of a mix may be required to fine-tune certain requirements. Okay, and that's why we do have a trial batch. After a mix design, we have a trial batch to make sure the results, the expected results are what we get, and then we will fine-tune the requirements. The variables under the control of the designer, which are material selection, cement paste to aggregate ratio, the water to cement or water to cementitious material ratio, the sand or the fine to coarse aggregate ratio, type, size, grading of aggregate, use of chemical and mineral admixtures. All these here, these are the variables that the designer can control to adjust to meet the requirements. Okay, the strength you do not decide, because this is based on the requirements from the owner of the job or the designer. The durability requirements the same way, but you have many things that you can control in order to manipulate these variables and come up with a mix that meet the specifications. Also, one thing to consider, as I mentioned, the quality control in the field must be considered when designing a mix, because you have to factor in the less than perfect practices. So on the other hand, when we're talking to contractors, to the construction teams, adhering to the sound standard, concrete practices will also help ensure that whatever mix designed will meet the requirements, assuming we have, done our part. So it's really a complementary process between, the designer who specify the mix, who specify actually the requirements, the mix designer who utilize, for example, whatever at his disposal here in order to meet the requirements, and also the quality control in the field. This actually will help sometimes reduce the cost, because if we do not trust 100% the practices in the field, I will over design my mix. But if we can ensure, good sound quality control procedures are followed, then I do not have to over design, for example. But, that's not the case always. So let's look at the methods, the mix design methods available. There are a number of different methods for mix design available. Although they are not directly comparable, they do give approximately the same relative proportions of the materials. And, they're all are capable of yielding basically suitable concrete mixes. The most common method used in North America is that established by ACI standard practice 211.1, and this is the method that will be described here in this class. So it must be remembered, however, that any design any mixed design method will provide only a first approximation of proportions. So these must be checked by trial batches, as I mentioned, in the laboratory or in the field, and then adjusted as necessary to produce the desired concrete characteristics. With any given set of materials, it may be found that considerable deviations from the ACI recommended practice may be necessary. So, and again, this is a recommended practice based on experience with where the many design tools have been established to help the designer. But again, these are recommendations, and you may have to deviate from such recommendation based on whatever best suits your situation. Okay, so once sufficient experience with local materials is required, these tables used in the ACI method should be modified to take their properties into account. So basically the ACI cannot really account for the materials that will be used in every locale on every job. So, and again, these tables and graphs are used to help you as a first try. And then you make any adjustments. Furthermore, as I mentioned, once you have developed enough experience with the materials you are working with, you can develop your own tables and curves that will actually fit your particular materials better. Okay? Okay, so as was stated earlier, the job specification may dictate certain mix requirements, such as the minimum cement contents and water cement ratios, slump, air content, maximum aggregate size, strength, the use of admixtures, or any other special requirements, okay? But regardless of the specification requirements, the establishments of the batch weights best, be accomplished by following the sequence steps I will show in the next graph here, in the next slide, I'm sorry. So this basically will ensure that the characteristics of the available materials are properly considered in combining them into the suitable concrete mix. Okay? So let's talk about these design process, steps. So in summary, the mix design consists of first determining the job parameters, aggregate properties, maximum aggregate size, slump, water cement ratio, and admixtures. Second, calculating the batch weights. And third, adjusting the batch weights based on a trial mix, made according to these calculations. Okay? So here basically a schematic of these mix design procedures or steps you need to follow. As you can see here, and this will I will go into this in details just after I finish this slide. The choice of a slump, maximum aggregate size, estimating the mixing water and the air content, selection of the water cement ratio, calculating of the cement content, estimation of the coarse aggregate content, estimation of the fine aggregate content, then adjustment for moisture, refer back to the aggregate lectures though, and then we do the trial batch, and if there is any adjustments we'll go back. Okay, so let's get into these steps in more details. Okay, step number 1, which is the required information. So before starting the mix design process, information is required on both the materials to be used and the structure into which the concrete will be placed. Raw materials properties include, as you can see here, the sieve analysis of both the fine and coarse aggregates, including the fineness modulus, the unit weight of the coarse aggregate, the bulk specific gravities, and the absorption capacity of the aggregates and the moisture content, and the specific gravity of the cement and the supplementary cementitious materials, mineral admixtures if used. Okay. Information on the structure includes the type and dimension of the structural members, the minimum spacing between reinforcing bars, the required concrete strength, the exposure conditions to which the concrete will be subjected. All right? You need all this information in order to design a mix. Okay? It may be handy though here, as I mentioned about aggregates, to go back to refresh your memory in certain parameters about the aggregates, the bulk specific gravity, the absorption, and the moisture content. You will need that when we do the adjustments for moisture for the aggregates. Second step is the choice of slump. Usually slump will be specified for a particular job, to take into account the anticipated methods of handling and placing the concrete. However, where the slump has not been specified, appropriate values can be chosen from this table you see right here. Okay, which applies when basically the concrete is to be consolidated by vibration for this table. Concrete to be consolidated by vibration. All right. So as a general rule, the lowest slump that will permit adequate placement should be selected. All right. So this, however, does not mean that the minimum slump should automatically be chosen from this table. Okay. Adequate placement requires, the consideration of the job site conditions, which often leads to selection of a slump closer to the maximum recommended values. Keep that in mind. So it is becoming, increasingly common to design concrete for a lower slump and then increase it to a higher value using water reducing admixtures. So that's probably the common practice nowadays. So workability can be overcome, workability issues. Step number 3, the maximum aggregate size. Generally, the largest maximum size of aggregate available, and of course, to be consistent, consistent with the limitations to be listed, should be listed here. As this will minimize the required cement content. If you remember, we talked about the maximum aggregate size. The limitations on the maximum aggregate size are, as follows. First, for reinforced, or pre-stressed concrete, the maximum size may not exceed 1/5 of the minimum dimension between forms, or 3/4 of the minimum clear spacing between bars, strands, or bundles of bars, or between the steel and the formwork. The second, for slabs, the maximum size may not exceed 1/3 of the slab depth. Okay, these are described in detail in ACI, so if you want to refer to it. Okay, so having said all that, be aware of the following. So if it is shown by experience that it is possible to place the concrete without honeycombing or voids, these requirements may be relaxed. Okay, it has also been found that at a given water cement ratio, higher compressive strengths can be achieved with smaller maximum sizes of aggregates. There is therefore a trend toward the use of reduced maximum aggregate size, especially for high strength concretes. This subject we might discuss later, and not sure, but we might come across it. Also, in many areas, the largest sizes available are between the 19 or 25 millimeter, the 3/4 inch or 1 inch. So it should also be remembered that for a given job, it may be unwise to recommend different maximum aggregate sizes for different parts of the structure, as this may lead to confusion and increases the probability of error. So you want to maintain uniformity throughout the job, not to specify various maximum aggregate size, various mixes for different parts of the structure, unless there are other requirements. But if aggregates is the only difference, the size of aggregates, no, I would unify it all in one, based on one size, just to make sure I have uniformity, and I will reduce the possibility or the probability for error. Okay, step number 4, estimation of the mixing water and the air content. As we have seen in the fresh properties module, the workability is dependent primarily on the paste content of the concrete and the amount of entrained air and the maximum size, grading and the particle shape of aggregates, if you remember. So an estimate of the water requirement to produce different slumps for both air entrained and non-air entrained concrete can be obtained from this table right here, which is based on experience obtained over many years of practice. So it is, however, better to establish these numbers from experience with the actual materials in question, rather than, resorting to the use of this table. If you, as we said before, if you have accumulated enough information and data about the material in question, you could develop your own tables and curves rather than just using the standard curve in ACI. Okay, so when water reducing admixtures are used, these values from this table should be decreased according to the amount of water reduction anticipated. All right. This table here shows the approximate amount of entrapped air to be expected in non-air entrained concrete, and gives the recommended levels of air entrainment when required, for different maximum size of aggregate and for 3 different levels of severity of exposure. Okay, as you can see here. So really this is a very comprehensive table. This is for air entrained concrete. This is non-air entrained concrete. This is the slump right here, required slump, and of course, you know, gives you here the amount of approximate air, you know, to be that will be entrapped, as I just mentioned. So this is a good table though. Also, since there is a frequent pressure, you know, from, as I said before, from job site for concrete with more slump, you know, which is unfortunately often, you know, obtained by adding water rather by adding paste, leading to a high water cement ratio and lower strength. It is suggested that the trial batches of the mix used to develop the strength relationship, you know, be made to represent the most unfavorable combination of the air content and water content. Okay, that is, you know, both the maximum allowable air content and the maximum allowable slump should be used in these batches rather than using average values. This will help, you know, prevent overestimation of the strength. Okay. Okay, step number 5, which is basically the water cement or water to cementitious materials ratio when we use supplementary cementitious materials. So the selection of the appropriate water cement or water to cementitious material ratio may be governed not only by the strength, but as I said many times, also by durability requirements. Okay, so if we are considering, you know, based on the strength consideration, in the absence, you know, of strength versus water cement ratio data for the specific materials, a conservative estimate can be made for the expected 28-day compressive strength from this table right here. All right, that's unless you have your own data of water cement ratio versus strength. Okay. So when type 1 Portland cement is used either alone or even with together with pozzolan, this can be used, this table. Okay, so of course it is possible that the specifications may be based on a required strength at a time other than 28 days. As I said, maybe the time when the forms need to be stripped in order to reuse them, because that's money. Or the design may require the use of another standard type of Portland cement, you know, type 2, 4, 5, 3, whatever. Or the use of slag or large quantities of pozzolans. In these cases, you know, the table shown here on this slide is not applicable. So the designer must develop his or her own data for these cases, or when the design is governed maybe by flexural strength requirements. So this table, you know, works for type 1 cements with the use of, as I said, with the use of pozzolan. But when we use larger quantities or contents of pozzolans, when we use slag, when we use other types of cements other than type 1, and also when the specified strength is not necessarily the 28-day strength, maybe another age is specified, we cannot use this table. We have to develop our own table from data that we have accumulated or gathered. Okay. Okay, so also it is always more desirable to develop the appropriate strength, time, water cement ratio relationships for the materials, as I said, that are actually to be used on the job site, not necessarily a standard curve from ACI manual. In this way, the effects of admixtures can also be determined. You know, as you see, this graph here shows a relationship, you know, between strength and water cement ratio for a typical trial mix or a field data for both air entrained and non-air entrained concrete. So the best really is to develop curves similar to this from our own materials in our locale. That will be more appropriate than using the standard tables and curves. Okay, speaking of strength, let's just have a little segue here in order to look at specifying strength in more detail, which is basically the determination of the required compressive strength based on ACI 301. Okay, basically 301 for US units, 301M for SI units. Okay, so basically this is the required compressive strength, which is F prime sub CR. This is determined, based on statistical data from this table right here, which is as follows. So when the specified design strength F prime C is 5,000 psi or less, this is the formula to use in order to or these two formulas in order to get the required design strength. Okay, for over 5,000 psi, these are the equation. Okay, when we don't have test data available, we use the table 4233C from the ACI 301. Okay, that was based on SI units I mean US units. This one here based on SI units. So when the specified design strength F prime C is 35 MPa or less, we use these equations to get the required design strength. I mean the required strength of the mix rather. For over 35 MPa, these are the equations to use. Okay, so basically what we do here, we use the larger of the two values. Okay, when test data is not available, again we go to table 4233C. But it is extremely unlikely that you do not have enough data available. The ready mix suppliers working in your locale will have enough statistical data basically to develop these equations. And again, just you have to make sure whatever statistical data available pertains to your required mix. If it's not, then trial batches will have to be done, and based on that we will get our results. Okay, so we talked about the implication on strength. Let's talk about durability. So if there are severe exposure conditions, such as freezing, thawing, and exposure to seawater or sulfates, the more severe water cement ratio requirements of this table here, 10.4, may govern the selection of the water cement ratio. Okay, so it might be noted, as just more, just more information. Some standards may have different requirements. I know I'm following the American standards and the ACI requirement or recommendations. Maybe, for example, the Canadian standards will also call for different requirements. It has actually a more detailed guide to the selection of the maximum permissible water cement ratio and concrete strength and so forth and so on. What I'm presenting here is purely what's followed in North America based on ACI. Okay. In addition, as far as the durability requirements, this table shows the ACI requirements for concretes exposed to different concentrations of sulfates in soils or groundwater, which include a specification of the type of cement to be used, as you can see here. Okay, so these are good references actually to use in cases of various conditions of exposure. Okay. Okay, step number 6 is the calculation of cement or cementitious materials content. Once the water content and water cement ratio, from steps 4 and 5 are determined, the amount of cement or cement plus mineral admixtures per unit volume of the concrete is determined, simply by dividing the estimated water requirements by the water cement ratio. However, many specifications, in addition, require minimum cement content. Such a requirement may be used, as I said, to ensure satisfactory finishability, quality of vertical surface, or even workability. It may also ensure against low strengths due to increased water demand at the job site, which we said we should never add. All right. When a portion of the cement is replaced by a mineral admixture, the replacement can be made on the basis of mass, weight, otherwise, or volume, although the mass is the most commonly used method. Okay, since Portland cement and the admixtures, have different specific gravities, the values of the weight and volume percentages will differ. You have to be aware of that. We will actually, in the example, we will have a variation where we add mineral admixture, and we will see what we need to do. Okay, so the following relationships, allow for conversion between the weight fraction and the volume fraction. I will show these on the next slide. The weight fraction is referred to as the F sub W, and the volume fraction F sub V. All right. Here are these, the relationships basically. As you can see, this is equation number 1 for the weight fraction, and this is for the volume fraction. So as I said, FW and FV, which is the ratio of the mineral admixture weight to volume, respectively, to weight to volume of total cementitious material. G sub C is the specific gravity of cement, which is generally 3.15. G sub P is the specific gravity of mineral admixtures. Okay. In the example, we will show this, and it will be more clear. When calculating also the cementitious material content, it is easiest, to first calculate the total weight of the cementitious material on the basis of 100% cement only, and then to calculate the final weights of the individual cementitious materials based on the desired weight or volume replacement percentages. Okay, so on weight replacement percentage basis, the weight of the pozzolan, which is referred to as P, equals the FW, which is the weight fraction, times CT. CT is the total cement requirement. On the volume replacement basis, the fraction P will equals F sub V times GP, G sub P over G sub C times CT. And finally, the value will be, the 1 minus F sub V over C times CT, rather, I'm sorry. This is in the case of volume, and in the case of weight here, it will be 1 minus FW times CT. So all common mineral admixtures, as we said, have specific gravities lower than Portland cement. So when replaced on a mass basis, they occupy a larger volume than the cement they replace. Remember that. Okay. The next thing step number 7, which is the estimation of the coarse aggregate content. it has been found, empirically, that the aggregates having the same maximum size and grading will yield, workable mixes when used in concrete in the volumes shown in this table right here. Okay, this is, based, on a dry rotted weight basis. So for the same workability, the volume of coarse aggregate depends only on its maximum size and on the fineness modulus of the fine aggregate. The oven dry weight of the coarse aggregate, required per cubic meter of concrete is simply equal to the value from, this table right here. All right, multiplied by the dry rotted unit weight of the aggregates in kilogram per cubic meter, or the volume of the aggregate, in cubic foot per cubic yard, basically can be obtained by multiplying the appropriate value by 27. In the example we will do later, we will use both unit system, just, so that you're familiar with both of them. To convert, from oven dry to SSD weights, you multiply by 1 plus A divided by 100. So you are advised to refer back to the aggregate lectures we had earlier to refresh your memory on some terminology. Okay, so basically this is, as I said, this table, which is the volume of coarse aggregate per unit volume of concrete. And this is, the volume with dry rotted coarse aggregate per unit volume of concrete, for different fineness modulus. Okay, and this is the maximum aggregate size. It will be clear when we do the table, when we do the example. Step number 8 is estimation of the fine aggregate. So now we have established the weights of all concrete ingredients except that of the fine aggregate. So we can establish the fine aggregate content in two ways. We have the volume method, which is basically the preferred method. So as it is, somewhat more exact procedure, which requires a knowledge of the volume displaced by the various ingredients. That is, the volumes of the cementitious material, water, air, and coarse aggregate, are subtracted from the total volume. The difference is the volume of the fine aggregate. The weight of the fine aggregate can then be obtained by multiplying this volume by the density of the fine aggregate. Okay, the aggregate calculations, just described here, are best carried out using the SSD weights, but they can be done using OD weights. In this case, the coarse aggregate weight is converted to OD by measuring its absorption capacity and then using the OD, which is the oven dry bulk specific gravity. So this is really the equation we use for, calculating the volume. This is the absolute volume of fine aggregate, which is 1, assuming 1 cubic meter, minus that of water, cement, coarse aggregate, and air. If we are using, foot-pound units, of course we are using 1 yard, which is 27 cubic feet, minus the volumes in cubic feet, okay? As I said, the SSD weight for the fine aggregate, bulk specific gravity times volume in kilogram, or the bulk specific gravity times the volume times 62.4 cubic foot per cubic yard. This is in pound units. After we find the volume, we find the weight here. This is, we're talking about SSD weight. If we need to convert to OD weight, then we do the procedure we described before. Okay, the mass method or the weight method, this one is less common, or as I said, the volume is the preferred method, but this one requires knowledge of the weight, per cubic meter or cubic yard of the fresh concrete, which can often be estimated from previous experience with the materials in question. Failing this table can be used for a first estimate to get the weight of the fresh batch, the weight of the fresh concrete. Okay. After that, we apply these equations depending on which system of units we are using to estimate the weight of the fine aggregate. Okay, so these here, U sub M or U, are the weight of fresh concrete in kilogram per cubic meter or pound per cubic yard. Okay, the G sub A is the specific or the weighted average bulk specific gravity based on SSD of the combined fine and coarse aggregate, assuming reasonable weight proportions, of course. The G sub C is the specific, this one here, the specific gravity of the cement, which is 3.5, we said. The A is the air content. Okay, and the W or W sub M, which is the mix in water, of course, depending on the units we're using. Okay, this one's W sub M when you're using kilogram per cubic meter SI units, and this one when we are using pounds per cubic yard. Okay, the C is the cement requirements in kilogram per cubic meter or pounds per cubic foot. Okay, so if the first estimate of the weight of the fresh concrete is not very good, an iterative procedure may be required to obtain the weighted average bulk specific gravity. Okay, that's really the value we are trying to find here. Okay, the weight of the fine aggregate is then, after we determine that, is the difference between the total weight of the fresh concrete and the weight of the other ingredients. Step number 9, adjusting for moisture content of the aggregates. As we know, the actual water content of the paste will be affected by the moisture content of the aggregates. So if these are air dry, they will absorb some water, thereby effectively lowering the water cement ratio and reducing the workability. On the other hand, if the aggregates are too wet, they will contribute some of their surface moisture to the paste, increasing both the water cement ratio and workability, and reducing strength, and of course affecting durability later. So the effects must be estimated and the batch weights adjusted to take them into account. Okay, so the adjustments will leave the actual mix proportions unchanged on an SSD basis. Again, we discussed this, if you refer back to the aggregates lectures, we discussed this more in detail. Okay, step number 10 of the mix design procedure is, a trial batch. So now, having now estimated the proportions of all the ingredients, the next step is to prepare a trial batch using these estimates, using only as much water as is needed to reach the desired slump, even if it causes the permissible water cement ratio to be exceeded. So that's what we're talking here. This trial batch is to fine-tune the mix design and make any necessary adjustments. Okay, so this batch may be prepared in the laboratory or using full-size field batch, which actually I prefer. The concrete then produced should be tested for slump, unit weight, yield, and air content, as well as observed for segregation tendencies and finishing characteristics. So this trial batch really goes a long way to help you fine-tune your mix and anticipate any problems and know what to expect. So you make sure you mitigate any potential problems before you actually pour the concrete. Okay? The batch weights and the unit weights are then used to calculate the weight of each material per cubic meter or cubic yard, whichever system of units you are using, as actually obtained in the trial batch. And again, after we do the trial batch, the adjustments we do to the water cement ratio to any other weight of the ingredients, then will be done based on the trial batch. Okay. Finally, the 28-day or any other age compressive strength or flexural strength, if required, should be determined. Okay. So basically, this is the process. I mean, basically, it's a methodical process. It requires, though, some experience. I know it's methodical by using certain tables and graphs, but also it requires really some experience in order to make any necessary adjustments. Okay. So after that, we're talking about adjustments can now be made in the batch proportions for these requirements that were not satisfied by the original estimates, as follows. Maybe, just to give examples. For any deviation in the slump, a new water cement or water content can be estimated based on the observations that an increase or decrease of maybe 6 kilogram per cubic meter in water and will increase or decrease the slump by approximately 25 millimeter. Okay. If the correct slump is obtained at a lower water content, it is permissible to reduce the cement content to reach the design water cement ratio. Okay, consistent with any specified limitations on the cement content. And again, I said, we could lower it, but if there is minimum, you cannot go beyond that. If the water content must be increased to obtain desired slump, then the water cement ratio will be increased. In this case, additional cement must be added until the design water cement ratio is again achieved. Okay, or you have to redesign the entire mix. The second thing, if the desired amount of entrained air is not achieved, the amount of air entraining admixture should be re-estimated. So the mix in water required should then be increased or decreased, okay, by 3 kilogram per cubic meter for each decrease or increase of 1% air entrainment, because of the influence of the entrained air on workability. The third thing, if the weight method of proportioning is used and if the estimated weight of the fresh concrete is incorrect, this can be re-estimated from the unit weight of the trial batch, making allowances for the necessary changes in the air content. Number 4, any adjustment, will change the yield. You remember we talked about the yield and the fresh properties. So a new batch weights must then be calculated following, the procedure we just mentioned, step 5 on. Okay. So anyway, I will stop here for now. I mean, this will be the end of lecture number 29. Next time we will look at an example which actually will clarify in more details what we talked about, these steps 1 through 9. Okay, so thank you for watching, and I will see you next time.